Okay, we should start. Everything should be in place. Yes, good. So, what are we going to do today? I know you just went to through another lecture, so you didn't have much break. Uh, so let me know if you need an earlier break today. So what we're going to do today is, so far we've covered model quality checks for single agent models. We looked at inappropriate priors. We looked at inadequate learning, right? What was inappropriate priors was, for instance, if we do priors that are shaping the posterior in ways that we cannot justify theoretically. Uh, we looked at inadequate learning. That is, what if the posterior is not more confident than the prior? What about if the posterior doesn't seem to be able to move away from the prior, even if it's really trying? We looked at inadequate fit to the data. That is, we want to check, running posterior predictive checks, whether after we've seen the data, the model's assumptions about the data, the model's prediction for what the data would be, are biased in some ways. And we started looking at partially unidentifiable parameters. What is that? So we've seen that when we have a memory model that plays against a biased agent that is mostly picking right, it's really, really hard for the model to exactly identify what portion of that picking right is due to the bias of the memory agent or to the memory in which it represents the actions of the bias agents, right? And what we are going to do, we started a bit at the end of last Monday, but we're doing it the full day today. We're going to be building multi-level versions of our models, the biased agent and the memory agent. Uh, Through this, we will better understand multi-level partial pooling models, and we will find new exciting errors that Stan can output when we run complex models. But before, since we're roughly at halfway through the course, and I forgot my colors there, I just wanted to hear a bit of feedback on how the pace is going for you, right? If we're going too fast, if we're going too slow, if there are burning questions that you have a hard time finding the time or channel to express, and that sort of things. So, yep. Hmm. Cool. Thanks. Yes. Hmm. Yeah. Yeah. Yeah, exactly. And there is a lot of redundance, right? So you have the lecture, the classes cover stuff that we see in the lecture. Some of the code is the same. There's the course notes exactly because it's tough, right? We need to, I think, Lawitz and then Ida. Yeah. Hmm. Yes. Cool. Yeah. So yes. So I guess the question works. I need to give a bit more context and repetition. Yes. Cool. Anything that you would wish to change? Yes. Yeah. Yes. And that's partly because they evolve at different paces. Uh, but yes, that's absolutely a fine point. I might be more explicit about which chapter we are. This is chapter 6, multi-level models. Yes. Yes. Mm-hmm. So which kind of videos? Okay. Yes. Yes. No, and I have collected a few also that that's a good idea. I have never created a Padlet, so I'll try. If I don't manage, I'll send an email. Yes. Yeah, but it's nice to have it all in one place, right? Yes, ready? Yes. Yeah, good. Yes. Yes. Cool. More comments? Okay. So since I want to cover a lot of content, I'm gonna take this as roughly a mid-course evaluation. If you have additional comments, you can send them to me, put them on the Q&A, and then I will produce a small summary that we can take up at the end. And again, any comment, any suggestion, any critique, they can come running and we adjust the course. Cool. So here are some slides that we've started seeing last time, but just as a reminder, right? We are simulating data from a random agent with noise and a memory agent with noise. Why noise? Well, because the data that we would have in the real world is always going to be a bit messy. So we want to see whether our models actually can perform with a modicum amount of noise, right? We saw that to simulate, what we have is a binary choice in which the rate at which right is picked comes from a normal distribution, a parameter called theta, which is a normal distribution and is specific by agent, so that agent 1, 2, and 3 will have each their own underlying rate. We've seen that these individual agents are not independent from each other, but they actually come from the same distribution of theta, a theta of the population, meaning that on average, we expect that the population will have a certain propensity to pick right, which means that we expect that if now we collect data from 100 people, right, and we get a theta of 0.7 with a certain standard deviation, and then we go out and we collect 100 more participants from the same subpopulation, let's say cog-sci students, we would get roughly the same kind of uh, distribution. We wouldn't get the same individuals, the same individual distributions, but we would get roughly the same population mean. And what we can see here is, right, the parameters of the simulation. We have 100 agent, 120 trials. We have a noise of 0.2, which is quite high, right? We're really stress testing our model. We have a mean rate for the bias agent, which is roughly 0.8 on a 0 to 1 scale. And it's there on the screen 1.386 because we're working on log odds. We have a standard deviation of the rate in, again, log odds, that is 0.65. How did I determine it? I tried values in the log odds space, transformed them back to probability space, and picked something that had roughly a 0.1. Right. For the memory agent, we have two parameters, alpha or bias. Should have changed that to bias, and beta. Alpha is the bias, how much the agent would pick right if there was no evidence from memory. And beta is how much strength do we give to the memory, that is the previous choices of the others in driving our current choice. A high beta means that as long as there is a slight evidence for right in the other, we're going to pick right. A low beta, it means that actually it's only going to shift our probability a little. And we have two standard deviations for both. Then we set up our simulation, right? We loop through the agents. We generate the individual level parameter from the population level parameter. So rate would be our norm. We pick one from a distribution with a mean of mean rate and a standard deviation of rate. We do the same for alpha and beta. We initialize the vector for the choices of the random agent, the vector for the choices of the memory agent, and a vector for the memory state. And then we loop through the trials, right? The random choice is given by the random agent noise function. If this is the first trial, that's the same also for the memory choice. Otherwise, the memory choice is given by the memory agent function, right? We organize that all, we save all the parameters, and then we go to the next. Whoops. Then we can plot the agents, right? And here you can see how the random agent is working, how the memory agent is working. They're covering quite a broad range because we put some different rate, so a standard deviation of the population for each of the parameters, plus these agents are not deterministic, they're probabilistic, so very broad range. We look at the memory agents, and the memory agents are performing more or less like the random agents, which could point to the fact that they're learning. That's not necessarily so. And they seem to have a slightly broader range, right? Because they are learning from the behavior of the other, so there is an extra layer of noise. So there's the noise in the random agent. There is the learning, which is affected by that noise, and there is the noise of the memory agent, so it's more dispersed. We want to check whether the memory agents are actually learning, just to see whether we set up the simulation correctly. So what we do is we put here on the x-axis the true rate of the biased agents at the individual level. On the y-axis, we look at the general tendency of the memory agent to pick right. And if these two variables are correlated positively, the memory agents are learning the true underlying rate of the random agents. After 10 trials, right, we can see that there is already a positive correlation, but the data are a bit all over the place. Yes? Yes. So on the x-axis, we have that the biased agents have a true underlying rate, which is different individual by individual, for how often they're going to pick right. Right. And that shouldn't change over time because that's the true underlying rate. On the y-axis, we have the observed rate of picking right of the memory agent. And we want to see whether, first of all, it's picked up at all, right? If the two variables are sort of positively correlated, and whether we see a learning effect that is the correlation becomes stronger and stronger the more trials we see, right? Because the underlying strategy of the bias agent is not changing, so the memory agent with more data should be able to pick up better. And what we see is that after 10 trials, things are a bit all over the place, but there is a clear positive correlation, so it is learning something. Of course, it is kind of a sitting duck, right? It's a really easy target. The biased agent is not changing their underlying strategy, and they have quite a strong bias. After 60 trials, we can see that the correlation or the data points are still a bit all over the place, but they're getting closer to each other. There's less spread. Like there's no memory agent expecting the bias of the biased agent to be 0.1 something, right? And after 120 trials, it's still getting closer and closer. Right? In none of these cases, we see data along the diagonal perfectly. And we see that the correlation is actually stabilizing in its slope. It's just getting more and more precise at somewhat an angle from the true diagonal. Right. So the question is, why don't we see that over the course of 120 trials, the memory agents learn perfectly the true underlying rate? Yes, because of the noise, because both the biased agents are behaving with noise, right? And the memory agents are behaving with noise, and therefore the observed rate of the memory agents will be affected in the learning and in the production by these two sources of noise, right? Does that make sense? Good. Okay, now we sort of kind of sure, or we're reasonably confident that the simulation is working. So what we want to do is we want to prepare the data for Stan. From our data set of the simulation, we take which agent we are at and the random choices that are picked because now we start by building, forgot to say, the multi-level version of the bias agent because it's the simplest one. We'll start with the simple thing. And then we need to I need my markers. So what we have in the simulation is a very neatly organized agent, I guess, trial, and then choice. Right, 1, 1, 1, 1, 1, 2, 3, 4, 0, 0, 1, 1, etc. And then we have agent 2. And again, we start from 1, 2, 3, 4. And then the choice might be 1, 1, 1, right? This is the tidy version of the long format. But Stan really likes simpler structures within a list, right? So it actually wants a matrix, not a long format, but what we usually call the wide format. So what we want is basically a matrix, two-dimensional vector, two-dimensional array, same thing, where I don't want to get it wrong. Here we have trial 1, trial 2, trial 3 on the row axis. And then we have agent 1, agent 2, agent 3, etc. on the column axis, right? This code is taking the agent and the random choice and basically making it into a while format. Are you familiar with the pivot command? But basically, we're saying take the names, so the columns from agent, and take the values from random choice, right? So that the columns will be named after the agents, and the value inside each cell will be the random choice. Then we create the data, where we have the trials is the number of trials. We defined it at the beginning of the simulation. The agents is the number of agents. We defined it at the beginning of the simulation. And then our outcome measure, the choice, which, for historical reason is still called H, because the very first simulation that I built was hat or tails. We build it as metrics, and we take these metrics that we created above, and we say all the rows, and then we take the column 2 to 101, and I can't remember exactly what it puts in the first one, but if you check your metrics, you'll see that the first column is something different. It's the row number, I think. Yes. So because it's more efficient. So the idea is that here you have a lot of metadata already in the Tibble framework. Second, that you end up having lots of redundancy here. You have 1, 1, 1, 1 repeated 120 times, and then it says that's silly. And especially then when you have more complex things where each agent might have a different value of theory of mind as measured by task, blah, 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 right? Then that value is going to repeat it one time every trial, and that's inefficient. Yes. Yes. So what you would have is that the random choice is this, and then you would have something else, which is, let's call it, it's the, I don't know, I don't like that. Let's say perspective taking score, right? How good people are at taking somebody else's perspective. So we would have a vector of length agents, and we would just have the list of the values by agent. Separate, yeah. It would be an additional row here, right? That would be perspective taking score equal the values of perspective taking scores in the order of the agents. Yes, then we would do a second matrix. So because here we have one integer, trials, another integer, agents, a matrix. As we will see when we build the memory agent, we will also have other choice. And then we will simply have two metrics, one after the other, one for self choice and the other for other choice. You could then add like a 3-dimensional matrix there. Stan doesn't care. It just cares for you not to repeat the information, which is a pain in the ass for us, but it's also a good way of thinking through your data, right? You really need to make sure that things are in place. When we do, then the data block in Stan, right? We can see it's Stan because it says data, curly brackets, and then curly brackets at the end. We just mirror that. So we have one value that's an integer, and the lower possible value is 1. That's the trials. Another value that's an integer, and the lowest possible value is 1. That's the number of agents. And then we have an array with trials as rows and agents as columns, which is composed of integers. And it's called H because we keep calling it H. We could have also said that the lowest possible score is 0 and the highest possible score is 1. That would have been a nicer check on the data. right? These operation, right, where we need to think is when we create the data in R, right? Instead, we simply translate, mirror the structure. What am I doing here? Oh, this is just the same thing, right? What we have is this choice that is generated by individual parameter values, which are generated from a population, underlying population parameter level. And these population has priors, right? These population level parameter as priors, which could be informed, right? We could take these values from previous experiments. That makes sense. But the way we're running it now is we are simply constraining the space of possible values to discount extremes that would be implausible and to avoid that the Markov chain gets lost in the long tails of log-odds distributions. Right? That's another way of representing that, right? You have that the choice is generated through the theta. The choice is different on a trial by trial level. The theta is different on an individual by individual level. And then there's population level parameters, which are not at the subject or at the trial level. If we had two groups, we could draw a second platelet, third platelet that corresponds to the full plate you see there. And we would say that theta mean would be specific to G, that as to a specific group, and theta SD would be specific to G, which means that two different groups could have two different population levels. So how do we represent that instead? Well, we have a parameter stuff, parameter chunk, where we have a real number, which is the theta mean, and a real number that's always positive, lowest possible value is 0, which is the standard deviation of the theta. And we have an array of length agent, which has real numbers and a parameter called theta, right? What is this is the individual level theta, right? Because we're not just estimating the population mean, we're also estimating the underlying rate for each individual. We then have the model. I haven't managed to turn them on white background yet. I'll do that. It's the model chunk. We have the two priors for the two parameters. We have a prior for the theta mean, which is a normal distribution log probability density function with a mean of 0 and a standard deviation of 1. And we have a prior for the theta standard deviation, which is a normal distribution log probability density function with a mean of 0 and a standard deviation of 0.3. Not going to do it here, but usually what you would do is you would visualize these in logout space and then in probability space to make sure that they're meaningful. But we've done that before with these exact numbers, so I'm not going to repeat it now. We do a small thing here that is we subtract from the prior of the standard deviation of the theta the normal log complementary cumulative density function, which is a trick that we use to say the prior should start at 0. It's a complementary distribution which basically takes down to 0 the probability of any value below 0. Yes? Yeah. Oh, yeah. So the idea is, imagine that, I need different color. Imagine that you have, nope. Imagine that you have distribution, which is centered at 0, has a standard deviation of 0.3, which means it goes roughly to 1 and -1, right? And the complementary distribution is a distribution which basically what you can do is you can say there it says that it starts at 0 and it does like this because it has the same mean and standard deviation. And when you subtract those two, these goes to 0. So all these part gets deleted. It's a statistical thing. I don't think it has any theoretical motivation beside the fact that sometimes we need to negate certain parts of the probability density function or mass function. And then there's a ton of literature that tries to define what's the actual formula that allows you to generate complementary distributions. I haven't looked at that because Stan does it for us, right? The extent to which I use it is simply to tell Stan whether distribution should be truncated at a certain level. Then what we have is a second, yes? It's not turning into a 0. Yeah, it's just completely out of, yeah. I should actually at a certain point maybe look into the formula and make a slide on that. That's a good idea. But the practical effect is it truncates the distribution. Okay, so we have a prior for the population level parameter, but we shouldn't forget that the way that individual level parameters are constrained by the population is that they're sampled from the population level, which means that the prior for theta is again a normal distribution with as a mean the mean of theta and as a standard deviation the standard deviation of theta, right? It's exactly this idea, right? That distribution has those priors for the parameters, these individual level distribution as the population level distribution as a prior, right? Meaning that individuals are a combination of what the data tells us and what the other participants tells us, right? And then what we have is that for each of the agents, for I in 1, 2 agents, which is the number of agents, we have a Bernoulli distribution on the log scale in which the choice H in the column I are generated by the parameter theta I. That is, all the choices for agent 1 are generated by the theta for agent 1. Yes. Yes. So some of it we discussed. That is, we think through, right, what the parameters are, right? So for instance, here it's pretty, at this level of the choice, it's pretty straightforward because you have a binary choice that we model at a trial by trial level. So that's the Bernoulli, right? Yes. Then what we want to know is what should we put on theta, right? And early on theta, we put a beta, right? Because beta is distributed between 0 and 1. And it allows us to create uniform priors, which sometimes are nice. However, right, that approach, so if you ask Josh, Josh will keep using the beta forever, right? He'll just contort all the code to make it work also when we do multi-level. But in my own way of doing things, what comes more natural is that, oh, now I actually have individual level distributions which are, coming from another distribution, but can deviate, right? So we can write the theta for agent one as the theta for the population plus, I don't know, something ID one, right? A certain distance that the individual has from the population. And that means that if this one is nice and easy to bound between 0 and 1, because it's a rate, as soon as we add or subtract something, we risk going beyond 0 or beyond 1. Right? So a way of ensuring that no matter what we do, we stay between 0 and 1 is to say that we don't care the scales of these and that, because we say that that's all on log odds, which as soon as we've done whatever messy model we have inside here, we can then do an inverse logit, retransform it into a probability between 0 and 1. And that means that we get for free that the rate for any agent is constrained between 0 and 1. If we had a log or a reaction time that needs to be positive, right? Then we would want to do the same kind of operation, but on a log scale, because the log transformation only binds at 0, but not at the other end, right? So in other words, there's no lookup table, no cheat sheet that we can use to define these things. We need to think through what the boundaries are for the kind of inference we want to do, and then try to figure out what of the many statistical tools that are out there, statistical distributions, we can best use. It's, every now and then I discover new stuff that I could have used before, but it's also because if you are a true statistician, sometimes you even just develop your own distribution, right? You just say, oh, okay, I want to device, the distribution of the last one I looked up was the distribution of how many trials it takes me to get it right 6 times, given some parameters, right? And that is a variant of the geometric distribution, sometimes called the hypergeometric distribution, which was created for that very specific problem, right? But it's not something that is widely taught or wasn't available before this guy developed it at a certain point, right? So it's a question of familiarizing you with a few different models, looking at what choices models in the literature that you're reading are making, right? And then sort of building up your own toolbox of things. And again, by far most cases, there's no one best solution, right? There's different solutions. So here we could use the beta, or we could use the logistic, not normal, the logistically transformed normal distribution. Can I think of other ones? Well, an economist would just say, oh, if we're far enough from 0 and 1, we can just use a normal distribution and call it the linear probability function. In some cases, it works. It really irks my aesthetic sense, but there are many solutions that can work in different conditions. So I got it right. Yes. Okay. So we need then to create the generated quantities to ensure that we have all the nice variables at our disposal. So we have, again, what we do is we create a real theta mean prior, right? We create a variable where we can store the prior for the mean of the population theta. We create a variable for the prior of the standard deviation of the population theta. We create a theta prior. That makes sense. Sorry, I just need to. Oh, okay. Yes. Then for visualization purpose, as I was saying, right, we have now a prior for the theta mean, and we have a prior for the theta standard deviation, which means that the prior for the individual level agents will be the combination of the two. And that's what the theta prior is. This is before we see the data. After we've seen the data, we'll also have something like that, right? The theta posterior. Then we're generating prior predictions. That is what we think, how many trials we think that the model would pick as right choices without having seen the data, just given the priors. We do the same with the posterior predictions, and then we generate the theta m prior as a normal random number generator with the same parameters as before. The theta standard deviation prior as a normal lower bounded random number generation with a mean of 0, standard deviation of 0.3, and a lower boundary of 0. If you check in the code on the course note, that function is actually a custom defined function that I write. So I don't need to pull in a big chunk of code here. I can just define it early on. The theta prior is a normal random number generator with the theta mean prior and the theta standard deviation priors as parameter, which is then passed through the inverse logit. So we see it on the probability space. The theta posterior is the same, but it uses the theta m as estimated by the model and the theta sd as estimated by the model. Prior predictions use a binomial random number generator with the number of trials and the theta prior. The posterior predictions, binomial random number generator with the number of trials and the theta posterior, right? Now we're generating it at the population level. We could even take each single agents and generate prior predictions for agent 1, 2, 3, and 4. Posterior predictions for agent 1, 2, and 3, and 4, right? Good. Questions on this, right? Does the STEM code make sense? I know that until you code it, right, it makes less sense, but the general structure, right? Okay, we can then run this command, which I don't think we ran before. We take the samples that we fitted and we say command stand diagnose, which is please look at the Hamiltonian and tell us if there are any issues. And this says checking sampler transitions tree depth, meaning our algorithm was sort of trying to look into the future to avoid doing U-turns. Did it have to stop, right? Was it still in doubt as to whether it would do a U-turn when it reached the limit of the tree depth that we set? And here it says tree depth is satisfactory for all transitions. We shouldn't worry about that. Then it checks the sampler transitions for divergences. And if you remember, divergences are when the physics of the underlying simulation breaks, meaning that I look around myself as I'm sampling. I see that I should go that direction because the log probability is becoming better. I have a certain velocity. I add, what the slope would lead me to think. I make my step, and then I can calculate, is the log probability that I have at this point what I would expect from my previous velocity and the slope? If it's not what I would expect, right, it means that the gradient changed in the step that I've done, right? So that my ability to explore the gradient around me was not good enough. I made a step that's too big, right? And that means that I'm not exploring this space efficiently. And the model says this is called a divergent transition, right? It diverges from my expectations, and we should mark it because it can signal issues, right? But in this case, since it's the simplest possible model, it works. Right? We look at HMC potential energy, which is kind of like the divergence, but when there are discrepancies between dimensions, it's just the same kind of operation. When the space, the posterior space, is probably not explored effectively. We'll see an example. Effective sample sizes is as I'm moving into my posterior space, I can look at how closely related my successive steps are, right? So if I enter here at small minimum, right, and I just keep bouncing around in there, then my successive samples will be very correlated with each other. I'm not exploring the space in an effective way. And therefore, what Stan does is says, yes, you've done 2,000 iterations, but really they count as two because you just went around and around and around, right? If the effective sample size is below 200, you get a warning, right? It says, again, you're not exploring the space in an effective way. Split hat R hat values satisfactory. What it does is it takes the Markov chains for each parameter, and it's saying if we split them at random, right? Are they similar to each other? Do they have the same mean and standard deviation? If they have exactly the same mean and standard deviation, we get a R hat of 1, which is perfect. They're exactly the same. If they diverge, they're exploring different regions of the space, or one is exploring better and the other exploring in a more constrained way. We get that their mean and standard deviation are not the same, and we get a R hat that's above 1. Here it's satisfactory, processing is complete, there's no problem detected. Great, I'm just very briefly showing this so we can take a nice break. Prior predictive checks, it checks out. Prior posterior updates, right? Here we have the population mean parameter, the theta m. In red, we see the prior. In blue, we see the posterior. In dashed black line, we see the true value. That's pretty much spot on, right? We look at the population SD parameter, right? We see in red the prior, in blue the posterior, in black the true value. And what we're seeing here is that the prior is slightly constraining, is regularizing the posterior, keeping the variability low, meaning that if there are participants who are more diverse than other participants, agents in this case, but what the model is doing is sort of pulling them towards the center because we believe that excessive variation might just be random, right? If these were participants, right, somebody is, I don't know, not really thinking when playing or didn't have coffee that morning or something like that. Or in this case, there's noise. Sometimes the noise hits more than 20% of the time, right, because it's a non-deterministic process. Here we have the rate, including the population level, what I was telling you here, right, the broader prior population level prior that includes the standard deviation and the broader posterior. And again, it's pretty spot on, right? Posterior predictive checks. In light blue, the prior predictions. In dark blue, the posterior prediction. And in black, the actual number. Again, pretty spot on. We could discuss whether that's precise enough, but at least we don't see any bias in the estimates. And here is how BRMS would visualize it, just because it's fun to look at it. And then we stop and we take a 10 minutes break. Good. Okay. So what we have is we're looking at whether the model works nicely. So far, we've seen that everything works nicely, but I just wanted to give you the full run of the quality check we've seen. So we can look at prior sensitivity of the model estimates. Again, we see on the top panels, 3 panels, 1 for each. Well, actually, so what we have in the top panels is on the x-axis is the prior theta from -1 to 1. We have that each panel is the prior for the SD of the population theta, 0.5, narrow, 1, broader, 2, even more broad. And then we have the dashed horizontal line is the true underlying theta parameter, 0.8. We can see that there are some variations, especially on the diagonal axis, as our prior mean goes from -1 to 1, but they are pretty much spot on, right? So our estimate of the population theta mean is really not affected in any meaningful way by the parameters, by the priors. We can look on the standard deviation of the population. Again, we see on the x-axis the mean of theta in the prior. We see here on the handle dimension the standard deviation of the population parameter. We see the dashed horizontal line, which is the true value, 0.65. And we see here that now we observe quite an impact of prior values, right? We can see that if the prior scale, so in the, actually I should write here, it's probably a bit confusing, but we have, I should throw this away. We have that the theta mean had 2 parameters, right? 0 and 1. And then we have that the theta SD, 2 parameters, 0, 3. The 0 is kind of not interesting to test because we would always expect it to start at 0. So we have 3 variations in the priors that we can explore. The x-axis is the mean of the prior for theta m. The panels are the standard deviation of the theta mean. And the colors are the standard deviation of the theta standard deviation. How confident we are that the participants will resemble the population. The higher it is, the more variations we expect. And we can see that with a very low level of variation, a very high confidence in all participants, all agents resembling the population, the standard deviation of the population that's estimated is biased towards 0, right? It's below the true value because we are being very strict about the model not having a lot of variation. If we start increasing it, 0.3, that's what we had put before, we see that the bias is still there, but it's much smaller. And indeed, that's what we were seeing in the prior posterior update checks, that the posterior was a bit below the true SD because the prior was constraining it. As we would increase it to 0.5 and 1, we see that it gets quite close to the true values, right? So we are seeing that our model here in the estimate of the standard deviation of the population is sensitive to priors.
in the region that we're using. We can then decide whether that's good. We're regularizing, right? We are expecting that some of the variation we observe in the data is due to noise, as we know it is. Or we could opt for a safer value. Right? That depends on the goal of your modeling. We can do parameter recovery. Again, I used only a bunch of parameter values. We have the true population means -1, meaning they tend to pick left, 0, meaning they're totally random, 1, meaning they tend to pick right. And then what we can do is we can play with how many agents and trials there are and see how well these values are reconstructed. We can see that 20 agent, 50 trials. The values are quite close to the diagonal, but they're not fantastic. We increase the number of trials. I'm not sure it actually gets better. Yes?
One thing I understood is zero and one.
Oh, yes. Okay, so what we were doing before is we were keeping our true underlying rate at 0.8 and true underlying standard deviation of the rate at 0.65. And the only thing we varied were the priors that we were using. Now, we can accept or not those priors, right? Let's say we accept them because we think that they don't really matter for the population mean, and they're doing a bit of regularization against the noise of the data. And then what we do is we vary the parameters of the simulation, not of the priors, but of the simulation, right? Exactly. Yep. And so we have that the true population mean is -1 in log odds, which corresponds to about 0.3 in probability space. And so on and so forth, right? And then we want that the estimated value raises together with the true value, right? That the model is able to perfectly estimate on the diagonal the values that we inputted in the simulation. And what we see is that with 50 trials, 20 agent, it's a bit all over the place. We increase the number of trials to 100, and it's still a bit all over the place. We increase the number of agents to 50, but still keep 50 trials, and it's still a bit all over the place, right? We need to increase both to get slightly better results. And what we see above is the recovery of the true population mean, and below the recovery of the true population standard deviation. Again, as before, we see that the population mean is easy. Even with 20 agents, 50 trials, we're quite close to the diagonal. But the standard deviation is hard, right? Measuring the heterogeneity of something is harder than measuring the average value, right? And so depending on how important the heterogeneity estimate is, then you can decide whether things are good or bad. The last thing I want to do as model quality for this model is we focused on the population level parameters, but we have also the individual level parameters. They might be important because sometimes what we're really interested is not whether people with depression, right, worse at, they respond more to negative feedback in the reinforcement learning paradigm, but we want to know what is the individual variability And does it correlate with something else? Like, is the amount of medication that they're getting, right? Is the medication affecting also that, if we think that that's the source of the atypicality in behavior? Or does it correlate with working memory, which is a nicer workable handle than just depression per se? We know that depression impacts cognitive function. If we specifically connect unwanted behavior or a pathological behavior to working memory, then we can actually have a much better target for intervention. And so we want to see whether the model doesn't just reconstruct the overall population mean, but actually the individual thetas. So here I put, I can't remember how many, 10 random subjects. And I put in red the true underlying rate of the simulation. Given that there is noise and I wanted to assess how much noise was impacting the estimates, I put in green the observed rate, right? I take all the 0 and 1s, I make an average, and then I have the observed rate. And we see in blue as a distribution the estimate of the underlying theta. Anybody wants to read the plot? What do you read from that? Right. So first, the model is not too bad, right? Everything seems to be relatively in the right spot. Of course, what we're seeing is that the model is fitting the observed data, right? It's fitting to the green dashed vertical line. So the model is not perfectly reconstructing the true underlying rate because it's assuming that the data we're seeing are clean of error. Right? We're not saying anywhere that there is error in the model. Yes. Yes. So let's say that you have an underlying rate of 0.8. So you tend to pick right 80% of the time. But as in the simulation, 20% of the time, one of the 5 trials, your mobile beeps and you get distracted. And then you just, and you pick something at random, right? So these, even if we have that the true underlying rate is 0.8, your behavior will actually have an underlying rate that's going to be a bit below 0.8 because of this noise. So if you were paying attention all the time, you would play with 0.8. Right? Because I created the simulation.
No, it's empirical rate is not like.
No, it's everything is still simulated, right? But it's since the true underlying rate only determines the choice when the noise is not acting. The observed choices of the simulated agent have actually a different mean, if you take the 0 and the 1s, right, than the true rate without considering the noise. Well, so the model that we have now is like all the models that you've applied so far in all your courses, that it's taking the data at face value, right? It's not questioning whether there is a noise term. And then it's saying whatever I cannot fit in the data must be noise, right? The residuals. Right? And here we're visualizing that the true parameter, if the agent was always paying attention, is not always the same that we could infer from the empirically observed data where a noise process takes place, right? Where the behavior is not always a precise and exact expression of the cognitive process. And that's what happens, right? Because you get distracted while you're running an experiment, or some trials, you have an intrusive thought, and sometimes you don't. And some trials you fudge and push the button too fast and didn't have time to look, right? So here we see that the model is pretty good at fitting the empirical data. That doesn't mean that it can reconstruct the true value because there's noise and we haven't learned how to deal with noise yet. Does that make sense? Good. Now, this is another visualization. We take the true rate of the individuals on the x-axis for all 100 that we simulated, and we look on the y-axis at the estimated rate. We see that they're pretty much on the diagonal, but just for the fun of it, I color in red those subjects or agents for which the credibility intervals or compatibility intervals don't include the true value, don't cross the diagonal. Right. Here I was playing, I'm not sure it came out very intuitive, but here on the right panel, I was playing with a different way of visualizing the error and estimating the different participants. And you can see that in red is the true rate, the red cross. In green is the empirical mean of all the choices. And in blue is the estimate with the confidence or credibility intervals or compatibility intervals. The 95% of the posterior sample. And you can see perhaps that I can't really see that much in this one, and that's why I made another simulation, another representation. You can see here that the further they are from population mean in blue, the more they get warped away from the diagonal, right? The more they get regularized. This is technically called shrinkage, right? It's what we do when we don't take the data at face value, but we say if a lot of the other participants are here and you're very far away, we're going to pull you a bit towards the rest. And again, here I really was playing with different ways of visualizing these data to understand the model, right? Again, there's no standard, right? But it's good to play with these things to understand your models. And I hope to give that this gives you some examples. So what would be missing is in parameter recovery and prior sensitivity, I didn't add uncertainty, but the posterior estimates are always uncertain. There's a whole distribution. We didn't really look at prior sensitivity and parameter recovery at the agent level in a serious way. But what we get is that we can nicely reconstruct the population mean, if that's the estimate of interest. We're not super good, but not terrible at population standard deviation. And individual rates, which generally are trickier, are actually, I don't know what you think, but if you look at the panel on the left, they're not too bad. Considering this is a noisy data set. 20% of the data is crap. Okay, now we've seen this on the simple model. Let's look at it in the complex model. We have the memory model that we've seen before, perfect memory, right? Two parameters, bias and beta. This is the representation. We have the choice and the other choice. The theta determines the choice. The other choice determines the memory. The memory determines the theta combined with the bias and the beta. The choices, theta and memory are at the trial level. The bias and the beta are at the subject level. And the priors for those are at the population level. Okay. We have the code. The only difference from before is that we're not just making a matrix of the memory choice, the own choice, but also of the random choice, the other agent choice. So when we prepare the data, we have trials, we have agent, we have one matrix, and we have another matrix. When we build STAN, again, that's the only thing that we just copy the line with in the array on choice, and we change on choice and say other. We have two matrices. Then we look at the parameters. Again, there's no big surprise. There's the mean for the bias, the mean for the beta, the standard deviation for the bias, the standard deviation for the beta, and two vectors. Individual level bias, individual level beta. We then have our memory state that is exactly like what we've seen before, but instead of just looping within the trials, we first loop by agent, and then we say for each agent, loop within the trials. And there's the model to be estimated. We have the prior for the bias mean, the prior for the beta, prior for the bias standard deviation with the log cumulative complementary function, the prior for the standard deviation of the beta, same thing. And then we have the individual level biases are sampled from a normal distribution with a bias mean at the population level, a bias standard deviation for the population level, and the same for the beta. Then when we calculate the likelihood, what we have is that you're first looping by agent, and then we're looping by trial. So the Bernoulli logic log probability mass function of choice at the trial, agent. Given by the bias of the agent plus the beta of the agent multiplied by the memory state for that trial for that agent. The logic is exactly the same as the model at the single level, the single agent model, but we are specifying that we're not just dealing with a vector of choices or a vector of memory, we're dealing with a two-dimensional matrix in which the rows are the trials and the columns are the agents. And then the generated quantities. I'm not going to go through that, right? What we do, right, is we run our model. It starts throwing some warnings, but then it says if these warning occurs sporadically, such as for highly constrained variable types, blah, 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 then the sampler is fine. Then we cross our fingers, we go and drink a coffee or a chamomile if you're stressed about the sampler, and then come back 1200 seconds after, 20 minutes after, and we say, oh, 20 minutes for this model, that might be a bit much. It also says 2 out of 2 chains at an energy estimation less than 0.2. And we go and look at the handbook, and the handbook says, well, anything below 0.3 is really bad. Okay. So we do our common stand diagnose. It says tree depth is not an issue. Divergences is not an issue. And by the way, actually, when I designed this example 2 years ago, it gave a lot of divergences, and I did it on purpose, and I was super happy because I wanted to talk about divergency. And then they improved Stan. It doesn't give divergences, but it still gives energy issues, right? So it says that BEBFMI 0.12 is below the nominal threshold of 3, which suggests that HMC, the Hamiltonian Monte Carlo, may have trouble exploring the target distribution. If possible, try to reparameterize the model. The effective sample size is satisfactory. The split our head values is satisfactory. So it's giving us mixed signals. Okay, we say, well, that parameterization thing seems scary. So let's do our usual quality checks. So bias M looks fine. Bias SD looks fine. Beta M looks not very good. So what we're seeing here is that the black chain is going up and down and up and down, up and down. And the blue chain is doing the same, right? So that there are actually, sometimes it crosses away from each other and then it crosses back. If it's a hairy caterpillar, it's two mating hairy caterpillars, right? We look at the beta SD, that's even worse. Right, the chains are clearly not overlapping. The chains are having trouble exploring this posterior space, just like EBFMI was telling us. Okay, we do our prior predictive checks. Nothing terribly bad. I like that my computer is telling me that I'm working now. Then we look at the parameter values. We see that the bias mean is overestimated. The beta mean is underestimated, but we're seeing exactly the same for the agent, right? So we don't know whether this is truly the issue. We see that the standard deviation of bias is overestimated. The standard deviation of beta is overestimated. We look at whether these parameters are correlated. And I don't think it's something I've introduced terribly well before. But the whole idea is that, as we've seen, that if I increase the bias, I can decrease the beta and get the same result. Right? If I increase my tendency to pick right in this specific test case where the other agent is mostly playing right, I can downplay the role of memory and get the same result. Or vice versa, I can downplay the bias, even give myself a slight negative towards that bias. But if I blow up the beta, I say I'm over relying on memory. As soon as there is evidence for right, I just pick right. I can get exactly the same result, right? So I can play in these directions, and there is no difference in the probability of generating the data that we're seeing. And indeed, when we look at how these parameters are correlated, we see that the beta M and the bias M are strongly negatively correlated. This is not always a problem, but we have other cues that there might be issues with exploring the posterior space. So these could be an issue. This is also another way of representing the correlation, right? The median of the correlation is minus 0.53 between the two. And we can see that it's solidly below zero, right? The negative correlation is very strong. This one was at the level of the population parameters. This was looking at the estimate for the individual agents. Okay, this is not too bad. It's the posterior predictive checks. Then we can look at the parameter recovery of the individual agents because there is a natural variability between agents. We can just look at whether those that have a higher bias are estimated as having a higher bias. Those that have a lower bias are estimated as having a lower bias. I think that's my look at the beta. Right? Not really that satisfying. So our model is having issues. If individual variability is important, as it often is, our model is crap at that. If population level are important, it's still doing decent jobs, but not ideal. Also, we get a strong warning that we're not exploring the posterior space well. So what? Well, energy is messed up. There's no divergences. We read the manual. It says, yes?
Which you just showed that the persistence is 72.
Yeah.
I think it's also like for assignment, I think we've experienced it's hard to determine whether it's the prior or if it's something you're doing in the model. So if you need to like determine if your prior is wrong, do you then just change it and go for everything again?
We do the prior sensitivity, yes. That's I showed for the previous model. Yeah. Right. So, but that's a great point, which leads me. So here I'm just saying what was messed up. Prior and posterior seems to be behaving though, right? They weren't too bad. We do a prior sensitivity check and we change adapt delta and tree depth, same issues. The model doesn't change. Right? And here is one of my favorite moments of the course. If you give me a second. And then that's usually my reaction.
Maybe we should just give up. I give up. I can't do it, gonna quit. Can't get through it, hit a wall, it's so impossible. When all I see are obstacles, afraid I'm gonna fail, and so I quit. There's no use in trying. There's no point. Don't give up. Don't give up. Gotta get right back up and try again. Mistakes can be breaks. Be way. Don't give up. Don't give up. Failure, your best friend. And try. Gotta get better. Try. Again.
All right. This I often hear that in the back of my head as I'm doing Stan, right? Yes. Okay. So we have our moment of discomfort, and then as you've seen in the small music video, as soon as they say we, right, it goes I give up, I give in, and then they say we, and something changes. They start pulling each other's up, and what we do is we start thinking, and somebody says, well, do you remember when we were doing our first models in Elamir or whatever is used now on methods 2? One of the things that we could do was standardize the predictors, right? The model didn't converge. Do you still do that? Yes, right? But so imagine again, we're moving in these two-dimensional space, say, for the posterior space. And we have that one of the predictors is how many krona somebody earns in a year. And the other is their score from 1 to 5 in extroversion, whatever, right? So the step that you're doing are going to be very skewed, because if you want to have a meaningful effect of how many krona you earn in a year, right, you need to have, you can have also a very small movement in the parameter space, and it can change quite a lot. But in the extroversion dimension, this door to window dimension, right, I actually need to make quite a big step comparatively for a small change or a change in that score to match, because it's a very different scale. And that might create issues in exploring these space. The two dimensions don't have the same scale, and that makes it tricky to explore. Scale it up to many different parameters, that can make it a mess. So what we learned in 2 and 3 is that we can standardize these scores. Right? We can z-score, divide them by the mean, subtract the mean, divide them by the standard deviation. We put them roughly on a -3 to 3 scales, both of them. And that means that the coefficients, the parameters that we need to explore, have roughly the same scale. Right? There's something that we can do here as well. So we need to mathematically transform the parameter space so that the sampler can better explore it. Sometimes we z-score the variables, but here, right, memory is already on a good scale, right? It's roughly between -3 and 3. It's in logouts. So we need to go deeper. We don't z-score the variables, we z-score the parameters. There's lots of that in the Stan handbook, which I recommend you go and check, not the 2.29, but the 2.36 version. And the key insight that you can say is that Stan really likes this normal scale with a mean of 0 and the standard deviation of 1, right? Which is the same thing that we do when we z-score the variables. So what we want to do is we want to change the parameters so that instead of just letting them vary however they want, right, they should be between -3 and 3. And this is also, that was my initial answer. Thank you, Stan, right? Can't you figure it out yourself? Why do I have to do everything? So now we have that our bias or theta or beta parameters that we were estimated are on a scale that is normally distributed with a mean of bias m and a standard deviation of biases. We need to create a function that transforms that into a normal with a mean of 0 and a standard deviation of 1. And if we think about how rescaling variables worked, we can use exactly the same procedure, right? We can extract the bias mean, making it into 0, simply by saying bias mean plus normal distribution of 0 and the standard deviation of biases. Right, that's just basic algebra. We take it out, and here we write 0. For the bias SD, right? Again, we can take it out, and now we have 1. We subtracted the mean, we divided by the standard deviation. Does that make sense? So here we have that the choice for trial by agent is given by the bias for the agent plus the memory state for that trial for that agent multiplied by the agent. The way that we want to define the agent now is, instead of saying that it comes from a normal distribution with a bias M of mean and the bias SD of standard deviation, is to do that transformation. So we say that the choice for trial, and agent is given by bias mean plus bias ID, individual deviation in the bias for the agent. And the same for the beta. We're building thing one step at a time. We're subtracting the mean, right? Then we say that the bias ID is a bias ID Z scored times the bias standard deviation. Right? Like we did that, like we took out the bias SD and say it has to be multiplied. We do the same here. That the bias ID here is given by a Z score, which is 1 times bias SD. And then we can say that, let's start from here, that the bias ID Z score is sampled from a normal distribution with a mean of 0 and a standard deviation of 1. Which Stan can run much faster. That works, but Stan can run much faster if you say that it's a standard normal distribution. Because the standard normal distribution in statistical jargon is the normal distribution with a mean of 0 and the standard deviation of 1. And it's slightly faster. At this stage, it doesn't matter much, but yes. So what we do now is that we say that instead of having a vector of bias at the individual level and a vector of betas at the individual level, we have a vector of bias ID Z scores and of beta ID Z scores. Then to the transform parameters, we say that we really want something called bias ID, that was in our equation, and beta ID, which is calculated by multiplying the bias ID Z score times the bias SD. Right. And then you can see here we have that the sampling of the bias ID Z scores from the standard normal distribution, and we have the likelihood where we have mean and the bias ID of the agent, where the bias ID has been decomposed into Z scored and bias standard deviation. Right. We run it, it still takes, oh no, that was before, right? It took 1220 minutes. It had a low BFMI. We run it again. Now it takes 15 minutes. Still an improvement. There's no warnings. Common diagnose is super good. We look at the prior posterior update checks. It's slightly better, not ideal, right? And I think that here the issue is really the kind of training data we gave it. right? It's really hard to identify these two parameters when the random agent is almost always playing once. So we could have better experimental design, varying random bias in opponents. We could have better priors, but I would be wary of that because constraining our inference too much post-hoc is kind of dodgy. When we look at the individuals, it's slightly better than before. At least it's not negatively correlated, but it's not very good. We don't have enough data in these specific experimental setup. We might try increasing the data. My suspicion is that we want the agent to play against a random biased agent with a varying bias. So reparameterization is an attempt at changing the shape of the posterior space so we can more effectively sample it. Is an old friend, right? We did Z-score our predictors, right? We saw sometimes that some of our variables were skewed on the right, and then we log transform them. When we did see that the outcome was a count, how many points somebody scored, right? Instead of using a normal, we used a Poisson distribution. We changed the posterior space. We changed the underlying equation that generates the outcome. And that changes the posterior space. We saw that the outcome is a rate between 0 and 1, right? We can do an inverse logit on the variable, or we can use a beta distribution, right? All of these ways are ways of shaping the posterior space. And I've been trying for a couple of years now to sort of see whether we can do like a more rigorous theory of reparameterization, but really it is a creative mathematical process in which a priori we can implement some of the knowledge we have into the model, right? Which kind of outcome is this, right? We look at the scale of our parameters. Are they on very different scales? We can sort of put them on the scale. But a lot of it is also done as we model. We explore the warnings that Stan gives us, and then we reshape the parameters to make sure that the posterior space can be explored. Right? The good thing about Stan is that it breaks fast and it breaks catastrophically, right? It tells you when things are wrong. And I think I'm gonna accept that you should make failure your best friend, where you can learn, as Ada Twist scientist is teaching us. And so what I wanted to say to conclude is that what I would like to try for next time is that I'm going to give you a homework as I anticipated, where there's a video with a lecture on model comparison that I gave last year. It's about 50 minutes. And I've remade all the course notes, so they should be much more explanatory. And then at the beginning of next Monday, we will spend the first part of the lecture with questions that you might have on that. And the second part, starting on Bayesian cognition, where we will also apply model comparisons. But these allows me to have everything that you need ready before we start also having some guest lectures in 3 weeks on concrete models that have been used to describe different kind of phenomena. See how it goes. The model comparison part is what is needed. I also put the mixture models because mixture models are an alternative and emerging ways of doing model comparisons, but we won't use them in the rest of the course. Cool.